recording. Okay.
Yes, sir, maybe.
Huh. Sure. So, okay, so let me carry on. So, suppose this is a kind of circuit. This is very simple circuit with one resistance and one switch. Okay, one voltage switch is connected here, right? This switch would be some power electronic switch. So this can be turned on for some time, and this can be turned off for other time in one time period, right? So, what would be the nature of waveform across this resistance, this P note? So that we will try to find out. So let us say this switch is on for d times of, let's say time period of t is there, and d portion of time period t is the moment for which this switch is conducting. Okay, so let us say dt is the period for which switch is on, and 1 minus t into t is the period for switch is off. Okay, so this scenario would be familiar, I guess, if you would have studied any buck converter. So this kind of scenario is there. So this is simple to that. Now, if I need to draw a waveform of V note, so what would it look like that I will draw here? So if you can see, so this waveform is also common with buck converter. So V note would be Vs for dt and 0 for remaining time of time period. Okay. Now this was fine. Either we can derive Fourier series for this waveform, or we can make a common waveform where we can derive or where we can generalize things, right? So generally, to recall about Fourier series, what it is, so I can write it as, it will have some average, right? Which is also known as DC, plus other harmonics from 1 to infinity, an cos n omega t, plus same for odd harmonic Tn sin n omega t. Okay. So if the waveform would be odd, then this waveform, this expression would give us zero, or this expression will be absent. And if the waveform would be even, then this will be absent. Okay. So by seeing this waveform, what do you think? Which kind of waveform is this? This is even or odd? Okay, so
Even
even. Okay, fine. Uh, how you can say it even? Because if
so
you
when xt is equal to x
my
minus t is equal to xt.
okay, so you are saying that xt is equal to minus of x minus t. So let us identify that if this condition is holding true here. So I will first take as uh, x of minus t. So I will do this operation on the waveform. So what I will get? I will get opposite of this waveform across the y-axis, right? So this should be dt, right? So this is your x of minus t. Now I will reverse it. So are you getting my point? What will happen? So do you agree? This will be minus x of minus t.
Yes, sir.
So it seems like it is not even function. So, but we can make it even function, right? If you want, you can shift it by some portion and you can make it even function. So I will do that, and I will generalize each and every waveform with even function, right? So, mm, so now it seems to be an even function, I guess. So if we can calculate Fourier series for this waveform, I think it would be good for many other waveforms. You will be just need some shifting and scaling. So let us say this was the voltage waveform of our initial buck converter, but it is shifted by how much? It is shifted by x of t minus, or rather plus, dt by 2, right? So right. So if this is even function, so bn terms would be 0, as I told that this term would be 0. I think it would be fine if I am just saying that Bn term would be 0. Because if you integrate it, then you will get that it will be 0. Let me also write the expressions of An and Bn. So An would be 2 by T, 0 to T by 2, xt cos omega t d omega t, like this. But we want to generalize it in terms of power electronics because this is a common expression in signal system and everywhere, right? But if we are focusing on power electronics, we should make our life simple because there are too many complications in power electronics. So what I will write in terms of angle. Okay. So generally time period is related to 2 pi. Okay. So I will identify it as 2 pi. And if it is 2 pi, then dt by 2 would become what? D pi, right? And this will become minus d pi, right? So this would be like that manner. So again, if and this value was Vs, right? So now I will calculate, I will write again in terms of An. So An would be 2 by T by 2, or you can say 2 by 2 pi, 0 to pi, xt, or this waveform of, okay, let us say xt cos n theta. I'm replacing omega t with theta, right? D theta. Okay. Now xt is Vs. Here xt value is Vs. This would be xt, so Vs would be this value. And we should not go for 0 to pi, or we can replace it with minus pi by 2 to pi by 2. We can take any limit within the time period. Any confusion in this? Okay, so if not, then we will go ahead. And so for minus pi by 2 to pi by 2, this period minus d pi and d pi lies within that limit. And hence we can write it as 2 by 2 pi Vs cos n theta d theta. And for the period when no signal was present, so that would be minus d pi to d pi, right? If you would have not wanted to transform with minus pi by 2 to pi by 2, you would have also done in that manner, that 2 by 2 pi 0 to 2 pi Vs, sorry, 0 to 2 pi, but 2 pi, there will not be signal for the entire period. So 0 to d pi Vs cos n theta d theta plus, since we are talking for the entire period, 0 to 2 pi, so this waveform lies for some more period. This is also period of d pi by 2. So we can also take that in account. So d minus d pi, or sorry, not t, 2 pi, because we are dealing in terms of angle. So 2 pi minus d pi to 2 pi again Vs cos n theta d theta. Okay, so I hope it is fine till now. So if you solve it, this expression, what you will be able to conclude that an will come out to be. I am not solving it for timing. I am just not doing calculation only. I have shown you this step. So I am writing the conclusion here. 2 Vs by n pi sine d n pi. So for any harmonics of this kind of waveform, you can calculate by this manner, right? It is very simple to calculate an. You prefer it anyway, but for this kind of waveform, and if it would be shifted like earlier, let's say it was earlier from 0 to 2 d pi, right? Why I am writing 2 d pi? Because earlier it is conducting d period for 2 pi times of time period, right? So that's why I can write it 2 d pi. And if I know the Fourier series expression for earlier one, I can also write for this one, and that would be 2 Vs by n pi sine dn pi, and this was the an, and now you want to write cos Earlier it was cos n omega t. Now it will be cos n omega t minus d pi. So it will be just shifted. If you know the expression or waveform for one common signal, you can conclude to any kind of waveform. So we will see the application of this as well. So any doubt till this point?
No, sir.
Okay, fine. Thanks. So moving ahead. So this was the waveform and Fourier series. And let me discuss a bit about buck converter as well, because this waveform is matching with buck converter. Okay. So let's say first let me make a new whiteboard. So if the circuit was like this, do you think this resemble with buck converter? Just a part of inductor and capacitor. Everything is same compared to conventional buck converter. Why? Because if the switch is closed for dt period, your voltage will get Vs. And if your switch is off, V0 will not receive any kind of voltage, right? So that's the similar thing happens in buck converter, just that capacitor and inductor tries to smooth the waveform and will got us the pure DC kind of thing at output what we require. Okay, right? So we derived above the Fourier series of that kind of waveform or that kind of circuit. So now, can we write Fourier series for this kind of circuit now? Complete Fourier series, not any extension. Like, so first of all, any Fourier series will have some DC, particular DC value, and that will be V not DC will be DVS, right? So we can write V not because when it is closed for D period, it will be DVS. So this is DC term for this way, this kind of circuit. But uh, some AC component will also be there. Okay, as we all know, this is a DC-DC converter, but some AC harmonic or ripple will be there. This the waveform. If you can recall, the waveform is kind of this. So if the waveform is of this type, then it will have some AC ripple. Okay, so Vs minus d pi d pi. Okay. Okay. So we wrote the average value of this waveform. You can also calculate. So that will come out to be dVs. Okay, average you can calculate either by area property or anything. So that average will be dVs. Now the time for the harmonics component. So from n is equal to 1 to infinity, we had calculated 2 Vs by n pi, okay, sine d n pi cos n omega t. So this is complete waveform of your output voltage. Okay. So I hope it is clear. Now I will go ahead and write current at the output. So current would be V naught by R, and that would be dVs by R plus n is equal to 1 to infinity. 2 Vs by pi, we can take it outside because this is constant value, and 1 by n sine dn pi cos n omega t. Okay. So we have calculated V naught, we have calculated I naught, and I naught will be equal to Is in this circuit, right? When I naught will be flowing, that will be Is only, right? So I naught will be Is. So I can write it equal to Is. Fine. So we know V naught, V naught, I naught. Then we can calculate it power. What will be the power, right? So power will be the multiplication of this V naught expression and I naught expression. I know you guys might be thinking that why this much thing is required in DC to DC converter, but this will be very helpful in inverter section, which I will be dealing very soon. So don't worry about all these harmonic terms. Just try to, fix it in your mind. So uh, I'm for sake of calculation, I am just going to write it V naught T into I naught T, and that will give you V naught square by R. If you even multiply this term V naught with I naught, you will get this DC component multiplication with this DC component, and that will come out to be D square Vs square by R, right? Plus some component of AC as well, and that I will write here. So that would be summation of n is equal to 1 to infinity. 2 Vs by pi should be outside. Sorry, 2 Vs by pi square into R. Okay, sine square dn pi cos n omega t. Okay, so sine has the component of pi, so it is multiplication of pi. So it should be zero, or any kind of integration with sine in a full time period, because this is harmonic component, and if you want to calculate the value, you have to integrate with 0 to t, so that will give you 0. So here you will get P naught is equal to d square Vs square by R. But if you see from input side, you will get some harmonic component as well. So that you will receive as VST into IST will be, if you compute, so Vs is same because Vs is DC here, but Is is equal to I naught. So now I will write Is as I naught. So I naught was, dVs by R plus summation n is equal to 1 to infinity 2 Vs by pi R, 1 by n sine dn pi cos n omega t. Okay, so this will be your Vs ist, and if you multiply here, so you will get dVs square by R plus 2Vs square by pi R summation n is equal to 1 to infinity 1 by n and dn pi cos n omega t, right? So your input average power would be this dVs square by R, and your output average power is d square Vs square by R. So, generally we consider ideal bus or ideal DC to DC converter where we say input power is equal to output power, but that is not the scenario generally. And this power, sorry, so this power would be generally lost in harmonic component. Excuse me just for a minute. So I hope this should be clear to you. If there is any doubt, then I would be happy to take. Because from input side, due to some AC harmonics, that RMS we consider, and due to that RMS value, you will get this dVs square. And even if you see at output side, if you take V naught RMS square by R and V naught RMS is equal to Vs into under root T. If you see this waveform, which I drew earlier, so if you calculate RMS for this value, you take this component and you take a period for d pi or something, d pi divided by pi, or 2 d pi divided by 2 pi. So you will get Vs under root d. So from that you will get d Vs square by r. So this was all about this kind of circuit, but we will use these expressions, these expressions. Importantly, this one is very, very important. It will come very handy. This one, this expression, I think you should either be perfect in solving instantly, or you can remember it as a, reference expression. For this kind of waveform, you can take this kind of expression as a reference so that we can use it anywhere. Okay? Because all power electronics circuit and waveforms are like a square type of thing. So you will be able to use this. So I hope this is fine. So I wonder, no any doubt, have you known this kind of waveform earlier? I just want to clarify. Anybody?
Yes, we knew the waveform, but the expression that you just told us that power is lost in harmonics, we didn't know that.
Yeah, yeah, fine. Okay. So this expression will be very handful. And if someone will ask you that uh, there is no loss from AC to DC, you now know that there would be some loss in harmonic component. So you can state that. Generally, at UG level, we generally consider as ideal, but nobody knows when someone would ask anything. So it is better to just keep in mind. However, we will use this expression very extensively in inverter, because in inverter there are so much waveforms. So we will deal with this expressions. So I think should I start something? Hmm. So I am again just generalizing the thing, whatever I have discussed earlier. So this kind of thing is called as switching function, and it is denoted as h, and it ranges from minus dn pi to dn pi, which would lie from or within minus t to t. Okay, and let's say its value is 1. Okay, so I'm just generalizing here. So h would be d plus 2 by pi, n is equal to 1 to infinity 1 by n sine n pi d cos n omega t. Okay, so this waveform, just I wanted to generalize. If anywhere some switch is there, let's say some switch is there, okay, some input is given, and here we are receiving some output. And the switch is like that, it is being closed for DT and being open for the remaining time of the time period. And this input current is also flowing from input side. So we can write it as V naught is equal to H times Vi, okay, and Ii is equal to H times I naught. You agree on this one? So if any switch is connected anywhere, we can just by seeing at input, we can write it at output just with the relation of this switching function, this H, right? This switching function is very important, and you will know that why it is so much important. It simplifies all the expressions and all the working operations of all the switch kind of things. Because in power electronics, only switches are there with which we will deal with, right? So let me take an example and then we will uh, conclude it for the day. So let's say this is the circuit here. Two switches are connected. This is V1, this is V2. This is working with H1 switching function. This is working with H2 switching function. And there is some inductive load with continuous current, and this is the node where we will find the value of output voltage. And you know it or not, this circuit you have seen. I can guarantee you this circuit you have seen. And why I am saying that, I will also explain that. I1, I2. So I want to know from you guys what will be the value of P naught. I want to write here the value of P naught. And this both switches are complementary. So one more condition I am giving, H1 plus H2 would be 1. Okay. So when this is working generally in power electronics devices, when two switches are connected across the same lane, both switches are generally complementary. So that condition is also being satisfied here. Now you can tell me the expression of V naught in terms of V1 plus V2. There is some value will come here. Similarly, uh,
H1 V1 plus
great, great. Yeah, you are correct. H1 V1 plus H2 V2. Correct. So that's it. And if you just replace V2 with, ground, or you just do it zero, it is nothing but your buck converter. Okay, so let's say V2 is zero, so this term is getting cancelled. That's why I told you that you know this circuit. And V naught will be H1 V1, and H1 average value is D, which is duty cycle. So you will get V naught equal to D V1. So this is very simple, right? So I want to know more about I1 and I2. What will be I1 and I2? Because I naught is known, right? In terms of I naught, I1 is equal to something I naught. Can anybody help me with this?
H1
H1 I naught and here H2 I naught, right? I2 will be equal to I naught when this switch is closed, and I1 will be I naught when this switch is closed and this is open, right? So this condition is satisfied. I think this would be interesting, and this is all regarding power electronic switches. And in next class, I will discuss something more about inverter or converters. But yeah, now I want to discuss two, three previous year gate problem, which is as tradition I have to discuss. So let us take one problem from that section. So this I will continue in next class. And now I am going to take one problem based on this buck converter only. So you might relate it with now with in terms of this switching function. So this is your problem here. This appeared in 2015 for 2 marks. Okay. So that V note when I was asking in that circuit, so that V note is nothing but this V note. Okay. And H1 is nothing but this switching function of this S, and H2 is nothing but the switching function of this switch diode, right? And here V1 is no V1 is 20 volt and V2 is connected to ground, so V2 is equal to 0. Okay, so whatever output voltage is here, you will get reflected at output terminals. So now we can calculate, because we need to calculate the charging current of the battery. So we need to calculate I naught here. That's it. So V naught will be equal to H1 V1 plus H2 V2. In any circuit, if you see it in this manner, it will be very easy to solve. And since V2 is 0, so this term will be 0. Now I need to find out H1, and H1 average value would be, you know, it is given the duty ratio of the switch S is zero point 0.4, so you can directly take as zero point 0.4 into, sorry, here it was V1 would be 20. If you calculate, it will come out to be 8 volt, fine. And 8 volt is here, that will come out to be here because average voltage drop across inductor is 0. DLDT would be 0. Okay, so 1 by T 0 to T. So that's why this VL average drop is 0. So whatever voltage you will see here, that you will see same at this point. So for that reason, V naught will come out here. And now we need to calculate I naught. So I naught will be V naught minus battery voltage 5 volts divided by that resistance 3 volts. So that will be 8 minus 5 by 3. That will be 1 ampere. 1 ampere was the answer for this problem. I hope you must have felt this question very easy now. So we will see. Any doubt there?
No, sir.
Okay, fine. So we will see one more problem based on this kind of thing. Yeah. Here the concept I have discussed today, it is similar to that now. So you can see here we have two sources and two switches. So before doing anything, I will first identify this switches as H1, this as H2. Okay. So this was also asked in 2015 for 2 marks. Okay. Now, now you can easily calculate this voltage, right? And in question, what is asked? The output voltage across RL. Very easy. Output voltage across RL. Earlier, you would have got confused if you see two voltage source here, but now you know that it is very common in switching circuit that V naught is, you will write it directly, V naught is equal to H1 V1 plus H2 V2, right? Now you just need to calculate H1 and H2 because you know V1 is given as 10 volt and V2 is given as 5 volt, right? So I can write 10 H1 plus 5 H2. Now the job is to calculate H1. Average would be D1, and this D1 is given, it is turned on for 0.2 millisecond out of zero point 0.5 millisecond, zero point 0.5 millisecond of, time period. It would come out to be zero point 0.4. So H1 you can put directly at zero point 0.4. Now the time for H2, H2 is turned on for 0.3 millisecond. The time is given zero point 0.5, so it will be 0.6. So now you just need to put this value 0.6 here and zero point 0.4 here. Your job is done. So 10 into zero point 0.4 plus 5 into zero point 0.6. So it will come out to be 4 plus 3, which is 7 volts. So 7 volt would be your answer. Wasn't that easy?
Yes, sir.
Yeah, thanks. So this was problem I just wanted to demonstrate here. And indirectly, I discussed DC to DC converter, not in great detail, but I think this would be sufficient to, you know, discover some basic problems. So, one theoretical problem is there with me. So, what is that? Yeah, please read the question. Uh, this is showing that primary MMF is least affected by secondary terminal conditions in a which transformer? Power transformer, potential transformer, distribution transformer, current transformer. Anybody knows the answer of this problem? So MMF is generally NI, right? So this is ampere terms. Least affected by secondary terminal means it will not change or it will not care about whatever is happening at secondary terminal side. So power transformer is generally voltage source transformer, right? So here your voltage will get transferred, right? Potential transfer, potential transformer, and this power transformer is connected at transmission lines. Transmission lines where uh, after generation the power is needed to transfer, but we cannot transfer. Generally, we do not prefer to transfer low voltage, high current kind of scenario through a wire due to obvious reason, the losses. So we always try to transformer or transform or transfer high voltage, low current. Okay. So this is generally accomplished with the help of power transformer. And again, near to your distribution node or distribution center, again it is getting a step down to low voltage or whatever required current. Okay. So again, it is brought down to the requirement level. So generally, it is in this manner. V V1 V2, I1, I2. So you all would have studied this basic transformer, single phase transformer, where how much amount of primary current can be drawn from the supply depends on your load, right? You know this. It varies on load. How much load is asking, that much supply will be transferred from the primary side to secondary side. Okay. So it is depending on secondary side. So this option we can eliminate. Excuse me. Yeah. So we will explore this potential transformer, and potential transformer is generally used to measure the voltage. Okay. So to measure the voltage, we generally can't measure very high voltage, let's say 1 kV or 11 kV. We can't measure this because even if you can measure, but it will take much higher price of voltmeters to make it very efficient. If you have any 11 kV voltage here, you transfer it with number of turns with 1000 times 1, so it will generally come out to be 11 volt, right? 11 volt you can easily measure, right? But again, it depends on your load because all voltage induced transformer depends on your load condition. So the potential transformer does, measure, does make easier to measure your secondary terminal voltage, but it is again depending on your terminal condition. So I will again eliminate it. Distribution transformer is nothing but whatever transformer you see in your local area where you get supply. So this is again voltage induced transformer. This transformer does not depend on load because this is current transformer, and whatever current is flowing to primary, okay, same with some turns ratio. Let's say it is you know 1 is to 1000. Let's say here 1 kilo ampere was flowing, and now you want to measure with ammeter at secondary terminal. So we will do the MMF balance. So 1 kilo ampere into 1 is equal to no current either. So let's say this dot just to make it fine. I2 into 1000. So you will get current is equal to 1 ampere at secondary terminals. And because it is dependent on current only, so doesn't matter whatever will be load, right? This load will get only that much current, whatever will be supplied from primary side. So it will not get affected by the load. So we can write it here. So now you know that this one is least affected by secondary condition. Fine, so these three problems, this was also asked in 2015, but for 1 mark only, because this was a bit theoretical problem. So any doubt in this problem or any of the above?
No, sir.
Okay, fine. So I hope and in next session I will continue that power electronic topic because we have time, so we will continue one topic and we will finish. And I hope you guys will like that approach of solving any power electronics or switching circuit generally. Actually, that thing being taught at IIT Bombay, professor teaches in that manner, and that becomes very easy. So that's why I thought that I can discuss it with you. So it will be helpful to you. I think I should wind up here. Thank you very much for your attention.
Thank you, sir.
Yeah, thank you. Welcome.
Thank you, sir.
Thank you. Thank you, FC.